Hello,
Yeah,
Harshit.
yes, sir. I'm audible. Am I?
Yeah,
Hello.
yeah, yeah. You're
Yeah,
audible.
actually, yeah,
Am I
I'm
audible?
audible.
Can you hear me?
Yeah, sir. I can see your screen also.
Okay, okay, fine. Okay, so we'll start shortly when others will join.
Can I get the yesterday's recording of the class? Yesterday's one.
Sorry?
Yesterday class. Actually, I couldn't get connected because of this network issue.
Okay, okay.
So yesterday's class, and I couldn't hear what you were speaking also due to this network issue.
Okay,
What
okay.
you were introducing, so that. Yeah.
Okay, so for that issue, okay, so for that you can, when the recordings will be uploaded, then please
Okay.
watch the recording for the
Okay.
first week, then
Sir,
you will
is
understand.
this 2 weeks? Is it in a 2 days class or one day class? Is this course? Because you
For
have
the,
mentioned week Saturday alone, no, sir. Saturday, I think.
no, actually it is Friday and Saturday.
Oh, Friday. Sir. Okay, sir. Okay.
Okay,
Okay.
Friday
Thank you.
8 to
Okay.
10 and Saturday 8 to 10.
Okay, sir. Okay. Thank you. Yeah, okay.
And you can ask me if you have any doubts regarding the last week which we discussed.
Yeah, sir. Sure, sir. Yeah, sir. Sure.
Hi Pranab. Yeah, so video for the recording they will give me an ID, right? So after that, once they will give me the ID, ISSS, then I will upload the recordings in that corresponding drive. Okay, and then you will get the link for the recording. So don't worry for that, you will get. Okay. Regarding PPT notes, I will send you both Friday and Saturday PPTs on Saturday. Like for example, today I will after this class I will send you the PPT for these two sessions. Okay. Let Vikrant and other person join, then we can start. Hello, hello. Am I audible? Hello. Okay, so
Yeah, sir. You're audible.
can you see the slides?
Yeah, yeah, yeah.
So fine. So we will start with the topic of this week, which is enzymes. So before starting, anyone has any doubt from the last session? If you have, then please let me know. Otherwise, we can proceed with today's topic. Okay, so hopefully the previous topic was clear to you. So, okay, so let's start with the enzymes. So, first of all, my first question is, what is enzymes according to you? What does it do? Anyone?
They speed up
Okay.
reaction and so enzymes are generally proteins
Yeah.
which can speed up the reaction as well as it can secrete some metabolic activity.
Okay. So, okay, fine. Correct. But can only proteins be the enzymes? Can you name any enzyme which is not protein? Is it possible?
I-
Sorry. Is it
no, sir.
possible?
I'm not remembering.
Okay. So others, any enzyme which is not protein? Enzymes which is not protein. Can you name or can you guess? So if you have heard about ribozymes, did you hear about ribozyme? Ribozyme is made up of RNA or RNA and protein. Okay, so in this case, RNA plays a role to catalyze a chemical reaction, right? So RNA acts as an enzyme. So for those cases, those RNAs are recognized as ribozyme, which are the example of enzyme which is not protein. Okay. So here we will first start with the topic name, which is enzyme as catalyst. What do you mean by catalyst?
First slide is not visible.
Slide is not visible.
Now it's visible.
Okay, is it visible or not? It's fine.
Now it's visible here.
Okay, okay. So what do you mean by catalyst?
Again, sir, slide.
Huh? Sorry. What do you mean by catalyst? Harshavardhan, what do you mean by catalyst? Whatever you know, just share your idea. What do you mean by catalyst?
That can speed up the reaction.
Which can increase the
Speed
speed
up
of
the
the
reaction.
reaction.
Yeah.
Okay, correct. In more detail, someone else want to say? Yeah, so basically the basic idea he has said, that is correct, that it will speed up the reaction. So in how it will speed up the reaction, if I will ask you, then the answer is it can lower down the activation energy. I think activation energy you know from your school chemistry, right? So activation energy for a chemical reaction to be happened, if a substrate is getting converted to the product, then for the thermodynamics, the energy of the product will be lesser than the free energy of substrate, right? Now in this case the reaction to be happened so that the S can be converted into product P, then for a in a particular chemical reaction, then uh, it needs to reach to the transition state, right? And this transition state, the energy which is required to reach into the transition state, that energy is called activation energy. Okay, so if there was no enzyme, right, if there was no enzyme, then the graph would be like this: free energy versus reaction coordinate. Right? So the without the enzyme, the substrate has to reach here, right? So that it can reach to the transition state, then only it can be transformed into product. So that has to be a requirement of something which will give that energy, or which is called as activation energy, so that substrate can reach to this transition state. Okay. So now if there is presence of an enzyme, then the enzyme will bind to the substrate to make this ES. E means enzyme, S means substrate. So this E and S will bind and they will make this ES uh, compound, right? And for that, the activation energy required is very less. If you compare with this and this, then you can see that this activation energy is very less. After that, from ES, the substrate will be converted into product to P, so it will make a EP complex, and then the product will be separated from the enzyme to make the product. For that also, active. Okay, so for this reaction ES to EP, the transition state it requires this is, so the free energy of the transition state is this. So so now if we measure the energy of transition state when enzyme is absent, that means when the condition is uncatalyzed, and when the enzyme is present, means the condition is catalysis, right? So in this case, this site is the delta G catalyzed, because here enzyme is present, and this length is delta G uncatalyzed, because here enzyme is not present, right? So now if you will see that this delta G uncatalyzed is much more higher than delta G catalyzed. That means if there is a enzyme, then the transition then the transition state required for the enzyme is very less than that of the condition when the enzyme is not present, right? So catalysis, for this case, enzyme is the catalyst here. So in presence of a catalyst or enzyme, the activation energy will be lowered, right? Without enzyme, this is the activation energy of delta G uncatalyzed, and with enzyme, the activation energy is delta G catalyzed, which is lesser than delta G uncatalyzed. So an enzyme, like a catalyst, it can lower down the activation energy. That's why the enzyme speed up a chemical reaction. Did you get it? Any doubt? So any doubt you have in this case? Okay. So here you can see this is an example of binding of a substrate to an enzyme active site, right? Here this is your substrate which is binding to the enzyme active site, and this binding site is almost complementary to the substrate, right? That's why a substrate can bind to the enzyme and they will make this ES complex. Then the substrate will be converted into product P. Okay, so here there is a very good example of how does enzyme work and how it lowers down the activation energy. This is a very good example. So in this first figure, this is your substrate, right? Suppose a metal stick is the substrate, and an imaginary enzyme stickase is being used here, and the goal of the enzyme is to break the substrate, right? For the breakage of the stick, you need to first bend the stick, right? So in this case, stick is considered as substrate. This bent stick is considered as the transition state, and the broken stick is considered as product, right? So in this case, the role of this chemical reaction is to break the stick, right? This is the job. So when there is no enzyme, then the substrate has to go to this transition state, right? And then again it will reach back to the product. So now this difference is known as the activation energy, or delta G uncatalyzed, where it will that is the amount of energy which is required to, yeah, so this is the amount of energy which is required to uh, take this substrate to the transition state, right? Now when we use enzyme which is complementary to the substrate, right, exactly, then this enzyme will bind to the substrate to make this ES complex. Now the problem is, as it is completely complementary, this uh, enzyme binding site is completely complementary to the substrate. Then, as the due to this shape complementarity, this compound will be very stable. As they are very stable, then their energy will be very less, right? For example, here from the substrate it will come back to ES, because this ES complex is very stable here, right? So the energy will be very less, even lesser than the product. Then to achieve the transition state, it has to go here, right? So now the problem is the delta G catalyzed when you are using a complementary enzyme. So in that case, delta G catalyzed will be very much high, even higher than the delta G uncatalyzed, where enzyme was not used, right? So here the enzyme, so this is the example. If that happens, that if the enzyme has perfectly complement shape to the substrate, then it will not speed up the reaction, it will delay the reaction, because for this case it will require more activation energy than the activation energy which was required when the enzyme was absent, right? So this is a case where enzyme will delay the reaction. Okay, any doubt in this case? You understood? Aditya and Kuldeep, you understood? Why will it delay the chemical reaction? Can anyone please confirm? Aditya and Kuldeep, you understood? Okay. So when the enzyme is completely complement to the substrate, then the activation energy will be increased. So it will delay the reaction. And the third case is when the enzyme complementary to the transition state. So enzyme. So in this case, you can see that this is a substrate and this is the enzyme. So now in this case, enzyme is not complement. Then yeah. So now the enzyme is not complement to the substrate directly, but when the substrate will achieve the transition state, means when the stick will be bent, then it will be complementary with the enzyme, right? After that, this enzyme will act and this substrate will be broken, right? So it will make product. Okay. Pranab, Kuldeep, and Aditya, any doubt in this case? Why complementary will delay the reaction, or can you explain? The reason is, as the enzyme is completely complementary to the substrate, then this ES complex will be very stable. So the energy will be very low, right? So now this difference or the activation energy, which is called as delta G catalyzed, is higher than delta G uncatalyzed. Means the activation energy when enzyme was absent. So now, because of the enzyme, the activation energy has been increased rather than decreased, right? So in this case, enzyme will delay the reaction, right? So now the case C, when enzyme is complemented to the transition state. So in this case, in contrast of this, the enzyme is not complementary to the substrate, right? So it will make the ES complex, but there is no complementarity. So now the from this ES complex, it will go to the transition state where the stick will be bent, right? Fine, the stick has been bent. Now the enzyme has complementarity to the bent stick, yeah, right? So now it is having the transition state where enzyme is complementary to the substrate or stick. So in this case, it will actually lower down the free energy of, yeah, so it has lowered down the the free energy of the transition state, right? This black color is the graph when you have not used the enzyme. For that case, this is your transition state. But when you are using enzyme, then this is this blue curve. This is the free energy of the transition state. So activation energy when we use the enzyme, that is del G catalyzed, is lesser than activation energy when we don't use the enzyme, which is delta G uncatalyzed. So as this delta G catalyzed is lesser than the delta G uncatalyzed, then the so in this case the enzyme has lowered down the activation energy, right? So this example where the enzyme will lower down the activation energy, so it will speed up the reaction, right? So when the enzyme is complementary to the transition state, then it can be used as a positive catalyst, which will increase the speed of the reaction. Okay, any doubt? Okay, so these are the reaction we have seen two cases where enzyme will delay the reaction and when enzyme will speed up the reaction. Okay, so now we will see that complementary shapes of substrate and its binding site in the enzyme. So this is an example of enzyme which is dihydrofolate reductase, and it uses NAD plus as the substrate, right, and tetrahydrofolate as a substrate. So this yellow is the tetrahydrofolate and the red color is the NADP plus. So they has the separate binding site in the enzyme. So this red color NADP plus will bind uh, to one binding site in the enzyme, and this yellow color tetrahydrofolate will bind to its different binding site in the enzyme, right? And these binding sites are based on, suppose for example this region of the enzyme is almost complementary for the substrate red, which is NAD plus, and this region is complementary for the substrate yellow, which is tetrahydrofolate. So that's why the substrate can bind to the corresponding binding sites in the enzyme. Any doubt here? So I hope there is no problem in that particular slide. If you have, please tell me. Okay, so now we will shift to the enzyme kinetics. Okay, so enzyme. So what do you mean by kinetics, Kuldeep? Kuldeep, are you there? The study of, okay, Aditya is saying the study of motion. Okay, motion. Yeah, it's study of motion for, but in the context of chemical reaction or enzymatic chemical reaction, what do you get from doing a kinetic study? Okay, you can try, just guess, and then you can share your opinion. That's how we will discuss here. So kinetics is suppose for a chemical reaction, right? So for the chemical reaction, if you want to measure that what is the rate of the chemical reaction, okay, how much substrate is getting utilized, how much substrate is required to get the maximum velocity of a chemical reaction, right? So those informations, if you want to know, especially the rate related thing, how fast is the chemical reaction or how slow is the chemical reaction, right? So enzymatic reaction is also a chemical reaction. So here the kinetics is measured by the velocity of the enzyme, initial velocity V naught versus the substrate concentration. So if we increase the substrate concentration, you can see if we increase the substrate concentration, then the velocity of the reaction, chemical reaction, will also be increased, and it will right, and if we keep increasing the substrate concentration, then it will approach to the maximum initial velocity, which is Vmax, right? So it is a increasing curve. If we increase the substrate concentration, the rate of the chemical reaction will also be increased, right? Initially it will increase rapidly, but after that uh, the rate of increment will be decreased, and then this curve will be flat when the reaction will reach into the steady state, right? That means when it will achieve the maximum velocity Vmax, right? So if you want to measure the velocity of a particular enzymatic reaction, then how will you do? So first of all, you need to know this equation where it is saying that E plus S, it will make ES, which is the equilibrium reaction, because I mean the reaction is running through the both sides, E plus S to ES, and from ES to and from ES to E plus S. So both of the forward and backward reaction is there. So K1 is the rate constant for the forward reaction, and K minus 1 is the rate constant for the backward reaction. And then after formation of the ES complex, what will happen is here this ES complex will split into E and product. The substrate will be converted into the product, and enzyme will be free. And as enzyme is a catalyst, and we know that according to the function of the catalyst, it will be unchanged before and after the reaction. So that's why the enzyme will be unchanged, right? So this is the first reaction, and this step from ES to E and P, this step is only forward reaction is happening here, and this is the rate limiting step. So rate of this entire chemical reaction will be dependent on this rate limiting state, means this step. So V naught, or the initial velocity, will be equals to K2 into ES. right? From the school chemistry, you know that rate of the chemical reaction is equals to rate constant into substrate concentration. So here substrate is the ES, so that's why V naught will be K2 into ES, right? So rate of ES formation will be so he so you can notice here ES is producing by E plus S through this K1 reaction, right? As well as right ES is breaking down to E and substrate in this direction K minus 1, and it is breaking down to E and P to this direction. So rate of ES formation is K1 into E into S, and E equals to, you can write ET minus ES, right? Here ET is the initial total enzyme concentration and ES is the enzymes which are binding with the substrate, right? So as E is denoting the free enzyme, in the free enzyme equals to total enzyme minus the enzyme which are bound with the substrate. So ET minus ES. And rate of ES breakdown will be the only so as I told you that ES is breaking down to E and S in this direction, and it is breaking down to E and P in this direction. So rate of breakdown will be K minus 1 into ES plus K2 into ES, right? So now as we know that at the equilibrium, at the steady state, the rate of ES formation will be equals to the rate of ES breakdown. So rate of ES formation K1 into ET minus ES into S equals to rate of ES breakdown, right? That is equals to K minus 1 ES plus K2 ES, right? So now if you do some rearrangement, then you will get K1 ETS minus K1 ESS. If you just multiply these things, right, and then will be equals to ES is common, so K minus 1 plus K2 into ES. Now you can see that if you take K1 ETS equals to K minus, so it will be equal to K minus 1 plus K2 minus plus K1 into ES into ES. If you take this thing to right side, and then if you try to write the expression for ES, then ES will be, if you take this thing here, then K1 ETS, right, divided by K1S plus K2 plus K minus 1. ES will be equal to this divided by this, right? If you take this thing here, ES will be this. So now again you can rewrite the ES equals to, you can take K1 common from the denominator, then it will be S plus K2 plus K minus 1 divided by K1, right? And this K1 and this K1 will be cancelled out, so there will be ET into S divided by S plus K2 plus K minus 1 by Q1. This term K2 plus K minus 1 by Q1 is defined as the Michaelis-Menten constant Km, right? So we can rewrite ES equals to ET into S divided by S plus this term is Km, S plus Km, right? So now as from this equation, the velocity of the enzymatic chemical reaction equals to V naught equals to K2 into ES, because this is the rate limiting state, and we have derived an expression for ES, that is this. So V naught will be equal to K2 into ES. So ES will be ET into S divided by Km plus S, right? So now what is Km? So Km is the substrate concentration where the enzymatic reaction will achieve the half of the maximum velocity, or V max by 2. So if you use this Michaelis-Menten equation, this is called Michaelis-Menten equation. If you use this equation, then in case of V, you will write V max by 2, because we want to find the substrate concentration where velocity will be V max by 2, right? So in case of V, you will write V max by 2. So this expression will be Vmax by 2 equals to Vmax S by Km plus S. This K2 into Et into S is, so this K2 into Et, that can be written as Vmax, because velocity will be maximum when this Es will be Et. That means all of the enzymes which were used, that is Et, right? Et is the total enzyme which was used. So if all of them will bind to substrate, and then that means if Et equal to Es, then the velocity will be maximum, right? So that's why this Et, yeah, so that's why the when Es will be Et, right? That means all of the enzymes which you use, they are binding with the substrate, right? So in that case, when Es will be equal to E2, then V equal to Vmax. So for Vmax will be K2 into Et. So in this case, K2 into Et, we can write it as Vmax. So V0 will be equal to Vmax S by Km plus S. Vmax X S by Km plus S. Now, as we want to find the concentration of S, where the velocity will be half of the Vmax, so then we can write the equation, and in the case of V naught, we can write the Vmax by 2, right? Vmax by 2 equal to Vmax S by Km plus S. Vmax cancel out, then half will be equal to S by Km plus S, right? So from this equation we will get that Km equal to S. That means the substrate concentration equals to Km at the substrate. When the substrate concentration is equal to Km, then the velocity will be half of the maximum velocity. This is the definition of the Km or affinity or the Michaelis-Menten constant, right? Any doubt here? Aditya and Kuldeep, any doubt till now? Okay, so there is no doubt. Okay, Kuldeep, you fine? as there is no doubt, so we can proceed. Avi Garg has joined, so welcome Avi. So already one session we have done on yesterday, that was about protein structure and function. So in this session we are talking about uh, enzymes. Okay, so so whenever you will feel problem in the session, you can ask. And
Okay, thank you, sir.
yeah, and the PPT I will send you yesterday and today's session. Okay, so you can go through that. If you have any problem, you can ask me in email. Okay, fine. So I think we can proceed further. Okay, so this is the game, right? So now we will see that as the substrate concentration equals to Km, then the velocity of the enzyme will be half of the maximum velocity, right? So now at uh, so this graph shows the kinetic parameters that define the limits of the curve at high and low s. So when the s is very low, right, then Km will be very greater than s, and the right. So this term in the denominator Km plus s, that will be equals to Km, right? So then you can write the equation as Vmax s by Km, right, here. So it will be simplified to V naught equal to Vmax s by Km when substrate is very low, right? So if you will plot the V naught versus substrate graph, then this is a form of y equal to mx, right? Where the V naught versus s, it will be y equal to mx, which is a straight line, which is a linear relationship, and the slope will be Vmax by Km, right? So it will be a straight line here at the range when s is very low, then the graph will be V naught equal to Vmax s by Km. So it will be a straight line with a slope of Vmax by Km, right? This is the graph, straight line. But when the substrate is very greater than equal to Km, when I mean in this region, when the substrate is very greater than Km, then again in this microdifferential equation, so Km can be ignored. So this time you can write as Vmax s by s. Km will be equal to 0. Or you can ignore the Km. This Km plus s will be s when s is very greater than Km. So the expression will be Vmax s by s. S and s cancel out. So V naught equal to Vmax, right? So when the substrate concentration is very high here, then V naught will be equal to Vmax. So it will approach the maximum velocity Vmax, right? So again, when the substrate concentration is very low, it will follow the linear graph V naught versus s, where the slope will be Vmax by Km. Normally it will follow this Maglius-Menten equation, and when the substrate concentration is equals to Km, then velocity will be half of the maximum velocity. When the substrate concentration is very low, when the substrate is very lower than Km, then it will be follow this straight line graph, and when the substrate is very greater than Km here, then it will follow the this horizontal line where the velocity will be V naught equal to Vmax, right? So you understood this part? Three different conditions of a substrate, how this equation will be changed. You understood? So now we will go to the next part. So that is a term as we defined the Km as the as Km equals to K2 plus K minus 1 by K1, right? So now this K2 is the reaction rate constant of the rate limiting step, right? And when K2 is very less than K minus 1, then the Km will be, because why? Because K2 is the step of the K2 is the rate constant of the rate limiting step, and rate limiting step is the slowest step of a chemical reaction, right? Slow step is the rate limiting step. That's why K2 will be very lesser than K minus 1, and this equation you can write Km equals to K2 by K1. Sorry, K2 is, so K2 is the constant of rate limiting step. So as it is the slowest step, then K2 will be very lesser than K minus 1. So you can ignore K2 here, and then Km equals to K minus 1 by K1, which is defined as the dissociation constant, or Kd, right, of the ES complex, right? So when K1, so when K2 is very less than K minus 1, then Km will be equal to K minus 1 by K1, which is defined as the dissociation constant. So if you were given with K minus 1 and K1, then you should be able to calculate the dissociation constant, or Kd, right? Now the way to compare the catalytic efficiencies of different enzymes, the best way to compare with the ratio which is known as Kcat by Km, right? And this term is called as the specificity constant, which is the rate constant for the conversion of ES to E plus P, right? In this step, E plus S is ultimately converted into the E plus P. So for this reaction, E plus S to E plus P, the initial substrate and the final product. So the specificity constant Kcat by Km is the rate constant for the conversion of the ES to E plus S to E plus P. That means for the overall reaction, right? So when substrate is very lesser than Km, then you can write this equation, the rate equation, as V naught equals to Kcat by Km into Et into S, right? So this is the catalytic constant, or the specificity constant. So rate equals to Kcat by rate equals to Kcat by Km when substrate is very lesser than Km in this region. When the substrate is very lesser than Km, then V naught equals to Vmax into S by Km, right? So this Vmax you can write as Kcat into Et, right? Why? Because Vmax is the maximum reaction velocity. So it can only be possible when all of the enzymes you have provided, which is Et, when all of these enzymes are binding with the substrate. When Et equals to Es, then you will achieve the maximum velocity. So if you will put the Et equal to Es, then you can rewrite the equation V equal to Vmax into S by Km. So instead of Vmax, you can write, here you saw, right? Here in the Vmax you can write K2 into Et. So likewise you can write for the case of Vmax, you can write the Kcat into Et. Why? Because when Es will be equal to Et, then all of the enzymes are binding to the substrate. That means the reaction will be having the maximum velocity. So now in this case, V naught equal to Vmax S by Km when the substrate is very lower than Km. Then in place of Vmax you can write Kcat by Kcat into Et, right? And then into S by Km. So this kcat by km, this ratio is known as the specificity constant or the catalytic constant, right? So the enzyme which will having the more value of this kcat by km ratio or specificity constant, those enzymes are more efficient. That's how you can measure the efficiency of the catalytic property of a enzyme. Okay, so any doubt here? Okay, Kuldev is saying no. Fine. Others? Okay, so we can move ahead. So now we will talk about the inhibition. So what do you mean by inhibition? When can an enzyme be inhibited? Any idea? What is inhibition? Abhi and Kuldeep, anyone?
Molecule binds to enzyme, sir.
Molecules?
Binds to enzyme.
Okay, bind. Then what happens?
Enzyme prevent working.
Then it will prevent the enzymatic activity, right?
Yes.
Yeah, correct. So, yeah, so that's how you can define the term inhibition. So there can be some molecules which are known as inhibitor. They can bind to enzyme in a specific site of the enzyme, and then it can uh, prevent the activity of the enzyme or inhibit the enzyme, right? So there are three kinds of inhibition: competitive inhibition, uncompetitive inhibition, and mixed inhibition. So what are the difference? Can anyone tell me what are the difference? Why are they different? These three kind of inhibition. Any idea?
No idea, sir.
Okay, no problem. So so for competitive inhibition, so I will explain all of the inhibition one by one. So please ask me if you have any problem. So for competitive inhibition, first of all, you should know this thing as we already discussed that enzyme and substrate E plus L S they will combine and they will make this ES complex, right? This and later this EX complex will be dissociated to EN product. So in this case, inhibitor can bind to the enzyme in a same binding site for the substrate. See, for this case, this active site, the substrate will bind to this active site and this inhibitor will bind to the same active site. So when the binding site for the substrate and the inhibitor are same, that is called as competitive competitive inhibition, right? So for this case, if the inhibitor is bound to the active site, then at a particular concentration, substrate cannot bind, right? Because that binding site is blocked by the inhibitor. But if you increase the substrate concentration, then it will give a competition to the inhibitor. So eventually, this when you will provide more concentration of the substrate, then they will replace the inhibitor with the substrate. So this competitive inhibition can be overcome by this competitive inhibition can be overcome by adding extra substrates when this inhibitor will be outcompeted. So there will be competition for this binds for the same binding site between the substrate and the inhibitor, right? That's why it is competitive inhibitor, because the binding site is same. Next is uncompetitive inhibition, where this where now this inhibitor will bind to this enzyme substrate complex, but at a different binding site. So find out the differences. Difference is, in this case, inhibitor will bind to the free enzyme, right, and at the same binding site of the substrate. But in this case, uncompetitive inhibition, the inhibitor will bind to the enzyme substrate complex at a different binding site. See here, right? So that's why, along with that, this inhibitor will bind to this ES and they will make a ESI complex. But for this case, enzyme will either bind to substrate or it will bind to inhibitor, right? So either it will bind ES or it will make EI, right? Based on the concentration. If the substrate concentration is more, then this form will be prevalent. If the inhibitor concentration is the more, then EI form will be prevalent, because here binding site is same. S and I are competing with each other for the same binding site. But for the uncompetitive inhibition, they have a different binding site, so substrate will bind, and when this ES complex will be formed, then the inhibitor will come and it will bind to the ES complex to make ESI complex, and the binding site for the inhibitor and the substrate will be different, right? So these are the main differences between the competitive and uncompetitive inhibition. Clear?
Yes, sir.
Yes, yes.
No, sir, no question. All clear.
Okay, fine. So the third part is mixed inhibition, right? So mixed, this name itself suggests that it is mixture of this competitive inhibition and uncompetitive inhibition. In competitive inhibition, inhibitor will bind to the free enzyme, and in uncompetitive inhibition, inhibitor will bind to the ES complex. And for the mixed inhibition, the inhibitor will bind to both, either with the free enzyme as well as to the ES complex. So this is fine. E plus S it will give you ES to E and P. Now inhibitor can bind to the free enzyme to make this EI complex with the rate constant Ki, or the inhibitor can bind to ES complex, right, to make the ESI complex with a rate constant of Ki dash, right? So this resembles the competitive inhibition and this resembles the uncompetitive inhibition, right? So that is the mixed inhibition. So from this diagram you can see that this is a free enzyme. So inhibitor will either bind to the free enzyme to make the EI complex, or inhibitor will bind to the ES complex to make the ESI complex, right? Here also the binding site for the inhibitor will be different, right? So the substrate and inhibitor will share different binding site, okay? But either it can bind to, for uncompetitive it will only bind to ES complex, but for the mixed inhibition the inhibitor can bind to either free enzyme as well as the ES complex, but at a different binding site, right? So is it clear, three of these differences? Okay. So now we will go to the double reciprocal plot, which are made for the enzyme uh, inhibitors. So here, yeah. So here, what is happening that first we will start with the Michaelis Menten where equation where V naught equal to V max S by Km plus S, right? So if we consider that uh, if we do some rearrangement, and then we can write it as 1 by V naught equals to Km by V max into 1 by S plus 1 by V max. So this, if you plot 1 by V naught by versus 1 by S, then it will be a straight line with the slope of Km by V max and intercept of 1 by V max. This straight line. Clear? So this is called the double reciprocal plot. When we plot the 1 by V by 1 by S, the slope will be Km by V max and the intercept will be 1 by V max. Right? So this is a double reciprocal plot, and in this case there is no inhibitor. Right? So now we will see what were the conditions for the double reciprocal plot or the Lineweaver-Burke equation when we will add the inhibitor. So now this plot can be used to test what kind of inhibition is this. Suppose you have an enzyme substrate mixture, and then you are using a particular inhibitor, but you don't know what kind of inhibition it is showing. It can be competitive, it can be uncompetitive, it can be mixed competitive. But what kind of inhibition it will do, you don't know. So for this case, you can use this plot, the double reciprocal plot or Lineweaver-Burke equation, to check what kind of inhibition is this. So this is the inhibition for, so this is the plot when there is no inhibitor is present, right? So now now we will see the changes in this plot, and we will use the three different kinds of inhibition: competitive, uncompetitive, and the mixed competitive. So for the competitive inhibition, the graph will be, initially it was 1 by V naught equal to Km by V max 1 to 1 by S plus 1 by V max. But in the case of competitive inhibition, the plot will be of this 1 by V by 1 by S. It will have slope Km by V max times alpha, and intercept will be same 1 by V max, right? Where alpha equals to 1 plus I by Ki. I is the inhibitor concentration, right? I is the inhibitor concentration, and Ki is the rate constant. So alpha is a term which is defined by 1 by I plus 1 plus I by Ki. So now you tell me that if you are using a inhibitor, that means this term will be I will be greater than 0. Then for this case, if you are using an inhibitor, then should the slope will increase or decrease? Kuldeep? The slope will increase or decrease? Can you use the mic if it is possible, Kuldeep? Actually, you can try. I mean, it may be wrong or right, but no problem. But I want you to try. Okay. What do you guess? Should the slope increase or decrease?
I guess, sir, it will increase.
Yes, yes, please.
I guess it will increase.
It will, yeah, very good. Why?
Actually, the thing is when I is increasing, then I divided by K1 is increasing. So overall value of alpha is increasing. So if alpha is increasing, then 1 by V naught is also increasing.
Yeah, means this slope Km by Vmax. Initially it was Km by Vmax, right?
So
But when you are using alpha, I mean, when you are using inhibitor, then alpha will be greater than 1,
increase. Yes,
right?
sir.
So this alpha km by Vmax will be greater than km by Vmax. So slope will be increased. So you are right. Very good. Very good. So for this case, the slope will be increased. And alpha equal to 1 when I equal to 0. When there is no inhibitor, then alpha equal to 1. But if you will increase the inhibitor concentration, for example, when you make alpha equal to 2, alpha equal to 3, then the slope will be increased, but the intercept will be same because intercept will be 1 by Vmax. So if after adding inhibitor, your slope is increasing in this way, in this manner, by times alpha, and if your inhibitor is yeah, so if your slope is increasing by the times alpha and your intercept is constant, then the inhibition is competitive inhibition, right? Understood?
Yes, sir.
Yeah, fine. And yeah, so next we will go to the uncompetitive inhibition. For the uncompetitive inhibition, the plot will be 1 by V naught equal to Km by Vmax into 1 by S plus alpha dash by Vmax, right? So in this case, again the alpha dash equal to 1 plus I by Ki dash. Here you can see in this case uncompetitive, the alpha dash will be 1 plus I by Ki dash. So now you can see that the slope will be same, right? Slope will be same because again the slope is km by Vmax, but the intercept is increased by the times of alpha. Initially it was when there was no inhibitor, the slope was, I mean the intercept was 1 by Vmax when the inhibitor was not present. But when we add inhibitor, then the intercept has been increased by times of alpha. Now it is alpha dash by Vmax, right? Now if you will add no inhibitor, then alpha equal to 1, right? Then again it will be 1 by Vmax, right? But if you use the inhibitor, then the intercept 1 by Vmax will be becoming alpha dash by Vmax. So intercept will increase, but slope will be constant. That means the lines will be parallel because slopes are constant, and the intercept will be increased. So this is your alpha dash equal to 1 when there is no inhibitor, but when you increase the inhibitor concentration, then slopes are equal because lines are parallel, but the intercept has been increased. For this case, alpha dash equal to 1, so this intercept was this 1 by Vmax, but when you add inhibitor, although the slope is same, but the intercept length has been increased here, right? Same here, right? So if after adding inhibitor your slope is not changed, if your slope remains constant and the intercept length is increasing, then that time that type of inhibition will be uncompetitive inhibition. Understood?
Yes, sir.
Yeah, very good. So then the remaining thing is mixed inhibition. So for that the equation will be 1 by V naught equal to alpha km by Vmax into 1 by S plus alpha dash by Vmax. Alpha and alpha dash, right? So the alpha equal to 1 plus I by Ki, right? And alpha dash equal to 1 plus I by Ki dash. So this is the equation for the mixed competitive inhibition. And then you can see that 1 by V equals to alpha km by Vmax into 1 by S plus alpha dash by Vmax. So now you tell me, for the mixed inhibition, slope will be changed or not, or it will be constant or increasing or decreasing slope.
Hello.
Yes, yes.
Sir, I am saying that slope will be changed and intercept will also be changed.
Okay, so slope will be increased or decreased.
Slope will be increased. If
Why?
the
Why?
it's same as competitive inhibition.
Yes, it is. See the term. Alpha came by Vmax. So without inhibitor it was came by Vmax. But with inhibitor it is alpha came by Vmax. So yeah, you are right. So for the like competitive inhibition, alpha is greater than equal to 1. So this term will be increased. Correct. And what about the intercept?
Like uncompetitive inhibition, when alpha is increasing, so the intercept will also increase.
Very good, very good. So intercept will also the intercept will also increase. So again, if you will see the plot, this is the case of no inhibitor, and when we increase the inhibitor concentration, then you can see the slopes are increasing, right? Slopes are increasing as well as the intercept is also increasing. For this case, the intercept increase. For this case, intercept mode increased, right? So both slope and intercept are getting increased. So in that case, the particular inhibition will be mixed inhibition, right? Understood? How to determine the type of inhibition by using this reciprocal plot? So again, in a summary, that for competitive inhibition, Vmax will be same, intercept will be same, but Km will be changed by alpha Km, right? So that's why slope will be increased. For uncompetitive inhibition, Vmax will be Vmax by alpha dash, so Vmax will be decreased, and Km will be Km by alpha dash, so Km will also be decreased, but the slope, the ratio will be same. Again, the ratio will be C Km by Vmax. So the ratio will be same, so the slope will be same Km by Vmax, but Vmax will be decreased by alpha dash, and Km will also be decreased by alpha dash, right? That's why you have seen that uh, 1 by Vmax, as Vmax is decreasing by alpha dash, then that's why the intercept is 1 by Vmax. So 1 by Vmax will be increased. So that's why the intercept will be increased for the case of uncompetitive inhibition. For mixed inhibition, Vmax will be decreased by Vmax by alpha, right? So that's why this slope has been increased by alpha, right? And the Km is also will be alpha by alpha dash into Km. So in a summary, in competitive inhibition, slope will be increased, intercept will be same. Uncompetitive inhibition, slope will be same, but intercept will be increased. For mixed inhibition, slope will be increased as well as intercept will also increased, right? So these are the properties of different types of inhibition. If you have any doubt, you can ask me till what we have discussed. Okay, so now we will proceed into the factors on which the activity of enzyme can depend, right? So here the first thing comes is pH. So first we'll discuss about the enzyme pepsin. So what do you know what do you know about the pepsin in your body? uh, where does it reside, pepsin?
Stomach,
Stomach. So what kind of pH is there in the stomach?
acidic.
Acidic. Very good. So that means the optimum pH for pepsin activity is acidic pH, right? So that you can see in this uh, bell curve where velocity, the reaction rate is in the y-axis and pH is in the x-axis. So when we see that pH is 1.9 or 1.8 before 2, then that, I mean, in that highly acidic pH, the pepsin has the highest uh, velocity, right? But when you will increase the pH, right? When you will move towards the neutral and then basic, then the activity will drop. So that's why acidic pH is the optimum pH for the enzyme activity. Again is glucose 6 phosphatase. What does it do? Glucose 6 phosphatase?
Uh, it's a byproduct in glycolysis.
Yeah.
No, no, no. It's a step in
Glycolysis?
glycolysis. Yeah.
It is not in glycolysis. Remember in
Uh,
which metabolism it is? Glucose 6
sorry.
phosphatase in gluconeogenesis, where they form glucose, right? So, so in this case, glucose 6 phosphatase, what does it do? From glucose 6 phosphate, it will make glucose, right? So it will make glucose from glucose 6 phosphate. So this enzyme has the optimum activity at pH equal to 7.8 here, right? So in the very acidic pH, it has no activity, and at the very basic pH, it has no activity. It has optimum activity at the pH around 7.8, right? So that's how pH can uh, modulate the enzymatic activity. So enzymatic activities are depending on pH. And here we will see the pH dependence of the chymotrypsin catalyzed reaction. So chymotrypsin is a proteolytic enzyme, right? So it will, if we will supply a polypeptide chain, then it will cleave the polypeptide chain at different at some particular amino acid sequences, and it will cleave the peptide bonds. So you can see that the velocity of this enzyme chymotrypsin, that is optimum at the pH equal to 8, right? And if you go to till, and from there if you decrease the pH, the activity will drop, and if you will increase the pH, the activity will drop, right? The K cat will be maximum at the pH equal to 8 because it has the highest velocity, highest activity as at pH equal to 8. So at pH equal to 8, it has the highest K cat, and after that the the reaction velocity decreases, drops. That's why this K cat remains constant, right? And 1 by km is just opposite to the uh, what should I say? Just opposite to the km is what? Km is what? Km is the substrate required to achieve the half of the maximum velocity, right? So, so less km means the enzyme has the more velocity, right? So 1 by km will denote that that the more 1 by km value will denote that the enzyme has the less activity, right? For example, here you can see at pH 4, 5, 6, 7, the enzyme activity is less, right? That's why, right? That's why the 1 by km is uh, flat line. And when after 8, when the enzyme activity started dropping, then this 1 by km also started dropping, right? So from this to curve, you can see that that if you go left, if you decrease the pH from 8, then the velocity will decrease and kcat will also decrease. And if you keep increasing the pH from pH 8, then the velocity will decrease and the kcat will be constant. So it has optimum activity at the pH equal to 8, right? Understood?
Yes,
Yeah.
sir.
Okay, fine. So for each enzyme, the pH is important, and apart from pH, there are some other factors. For example, temperature. For example, detergent, right? They are important for the enzymatic activity. For example, for proteinase enzyme, for the enzyme proteinase K, high temperature is important. 42 degrees Celsius is the optimum. Why? Because at the 42 degrees Celsius, the at the 42 degrees Celsius, uh, the target protein, the target substrate will be denatured. So the proteinase K will have the access to the peptide bonds, right? That's why this 42 degrees Celsius is required for the proteinase K enzyme. If you will decrease the temperature, then the protein will be, the substrate will not be denatured, so peptide bond will not be accessible, so activity will be less. And if you increase the temperature, then the proteinase K will itself be denatured, right? So that's why enzymatic activity will be low. So at 42 degrees Celsius, the enzyme activity will be optimal, right? So yeah. So after that, we will go to the induced fit uh, uh, mechanism, right? So induced fit mechanism of an enzyme. So anyone can guess what is the induced fit mechanism of a enzyme? Any guess you are having in your mind?
So no idea actually.
Okay. Kuldeep, you have any idea? Okay, fine. So in induced fit mechanism, so what happens when in a when a substrate is binding to its active site of an enzyme, then the enzyme changes its conformation, right? So enzymes will change after binding of the substrate. The enzyme will change its conformation. For example, hexokinase. Hexokinase we have read in which chapter? Remember, Abhi? Hexokinase. In the first step of the glycolysis, when
So
when
yes, sir.
remember, yeah. So in the first step of
Glycolysis.
glycolysis, the glucose will be converted into glucose 6 phosphate. That step is done by hexokinase. Here glucose, so at this C6 position, hexokinase will add and phosphate group from ATP to make this glucose 6 phosphate. First step of the glycolysis. So this is the hexokinase enzyme, right? So when the substrate is not bound, so it will be in a open conformation. But when the substrate will bound, well, here the substrate is glucose. When the glucose will bound to this active site of the enzyme, then the enzyme will change. If you can notice, the enzyme has changed its conformation, right? That so this binding site has been more narrow here, so that the substrate is caged here. Substrate is trapped here. Why? Because this binding site has become more narrow, right? So once once the substrate will bind, so the enzyme will change its conformation so that this binding will be more tight, right? So that is called induced fit. Initially it was not, but when the substrate will be bind, the substrate binding will induce the conformation change, right? So that's why hexokinase undergoes induced fit on substrate binding. Okay, understood?
Yes, sir.
Okay. Then we will go to regulatory enzyme. So from the term regulation, what do you mean by regulation? In generally, regulation is what is regulation?
The regulatory enzyme may be the enzymes which will regulate the production.
Which will affect the production.
Yes, sir.
Yeah, yeah, very good. It will affect or it will modulate. It will change, right? It may increase the reaction rate or it can decrease the reaction rate both. So the regulators which can increase the reaction rate, those are positive regulator, and the regulator which are decreasing the reaction rate, those are negative regulator. So here, this is your enzyme. Okay. So now in that enzyme, no modulator or no substrate is bound. So now this enzyme in a less active state. Okay. But when there is a modulator will bind, and one thing you can see that this is the active site and this is the substrate, right? So these are not complementing, right? So this substrate cannot be fit in this active site of the enzyme, right? So it needs a help from someone else. So this help will be provided by the positive modulator or positive regulator, right? So this regulator will come, and this enzyme has two domain. One is C domain, one is R domain. One C is catalytic domain where the substrate will bind. Another one is regulatory domain where the regulator will bind. So now in this case, substrate cannot bind to the enzyme, right? Because the shape is not complementing. So now this modulator, which is positive, that will come and it will bind to here in the regulatory domain, right? This will induce the conformation change in the active site, right? Now you can see, now after binding of this modulator, this catalytic domain at the active site, substrate binding site, the conformation has been changed. So now the substrate can be fit here, correct? Now because now there is a shape complementarity. So now this is so now this enzyme is more active when the modulator has been bound, right? And this conformation change will allow the binding of the substrate, right? So now it is active enzyme substrate complex. So now after that, this ES complex has been formed. So from this, the substrate will be converted into the product, right? So this is the role of the regulatory enzyme, which has the both catalytic and the regulatory domain, right? And in the regulatory domain, the positive modulator will bind, and which will of this binding of the regulator to the regulatory domain will induce the binding of the substrate. Otherwise, the substrate cannot bind. So that's why it is helping in this reaction, right? So that's why it is positive. This M is positive modulator, right? Any doubt here?
No, sir.
Yeah. Now, can any of you? I want any of you to come and just explain that what will be the case for the negative modulator. Suppose there is a negative modulator. So, can anyone wants to come and tell me what will be the case for the negative regulator?
If there is a active
Yes.
site for the substrate and negative modulator will bind, it will change the conformation and shape of
Where? Where?
the
Where it will change?
at the catalytic site,
Yes, very good. Then
and so it will inhibit the binding of substrate to the catalytic site.
excellent. Very good. Very good. So that is the concept of the negative regulator and the positive regulator. Okay. Could you understood this concept? Kuldeep, any doubt you have? Okay, I think it's fine. So, so now we will shift to the graph. Okay. So here we will see the substrate activity curves for the representative allosteric enzymes, right? So, so what is the allosteric enzyme? Same thing here as we discussed here. Allosteric enzyme is when it has a catalytic domain and the allosteric side and active side. This is the active side, this is the allosteric side. So the allosteric side, the regulator will bind, and then if it is a positive, it will enhance the substrate binding, and if it is a negative, as Avi said, then it will inhibit,
Inhibit.
yes, inhibit the substrate binding. So this is allosteric side, this is catalytic or active side, right? So these are allosteric enzymes. So now we'll see the substrate activity curves for the allosteric enzymes. So the first one, when there is no so when there is no regulator is used, then if you will plot this V versus S, V versus S, then you can see that at this K 0.5, for the substrate concentration is equal to K 0.5, it's like Km, then the velocity will be half of the maximum velocity, right? Similarly, for the Michaelis-Menten equation, we saw that when the substrate equals to Km, or the Michaelis-Menten constant, then velocity will be half of the maximum velocity. That was for the non-allosteric that was for the non-allosteric enzyme. But for this case, for the allosteric enzymes, which has a regulation site, for this case, this Km is called as K0.5. Right? The concept is same, means that it is the substrate concentration where the enzyme will achieve the half of the maximum velocity, right? So now this is the curve when you didn't use any modulator, right? And now suppose you are using the positive modulator, for example here. So it is increasing the reaction rate, right? It is helping. So if you use the positive regulator, then the K0.5 plus it will be lesser than K0.5, right? Why? Because that means the less amount of substrate is required to achieve the half of the maximum velocity when we use the positive regulator. So this curve is shifted to the left side. And if we use the negative regulator, then what will happen? For the negative regulator, more substrate will be required to achieve the half of the maximum velocity, right? This is the case for the negative allosteric regulator. For this case, the graph will be shifted towards the right, and the concentration at which the enzymes will achieve the half of the maximum velocity in the presence of the negative regulator, it is called as K0.5 minus. So K0.5 plus is lesser than K0.5 and K0.5 minus is greater than K0.5. So in this case, reaction will be inhibited. In this case, reaction will be more faster, right? So in this case, there will be left shift. For the negative regulator, there will be right shift. Okay. Yeah. So any doubt? So in this case, you can see that for all of these cases, the K0.5 has been shifted. For the positive regulator, K0.5 has been shifted to left. That means it has been decreased. For the negative, K0.5 has shifted to right. That means it has been increased. But the Vmax has been same. For all of these things, without regulator, with positive regulator, with a negative regulator, Vmax is same, right? For all of them, Vmax is same. Only the K0.5 is changed, right? K0.5 plus is less than K0.5 and K0.5 minus is greater than K0.5, but the Vmax is same. So this is an example where the Vmax, the maximum velocity is same, but the K05, but the K0.5 has been changed, right? Any doubt here?
No, sir.
Okay, fine. This is one kind of allosteric regulation. Another kind of allosteric regulation is where the Vmax will be changed, means the maximum velocity will be changed, but K0.5 will be same. So first again we will start with this curve where no regulator was used, right? So at K equal to 0.5 for this, for K equal to 0.5 and this is the Vmax for this curve when no regulator was used. This is the Vmax, right? So at K equal to 0.5 it achieved the half of the maximum velocity, right? When we use the positive regulator, then what will happen? The reaction become faster, so the Vmax will be increased, right? See, the Vmax is, so now maximum velocity for this case is lesser than the maximum velocity. When we add the positive regulator, then the maximum velocity has been increased, right? So but the K0.5 is still same. If you see, if it is a Vmax for the positive regulator, then this is the half of the Vmax. So again the K0.5 is same. So if I try to draw here something that for this case when there was no modulator was used, this is the K0.5 and this is your half of the Vmax, right? Vmax and this is the half of the Vmax. When we use the positive regulator, then Vmax has been increased. Now the half of the Vmax is this, okay? Because Vmax is, because when we add the positive regulator, Vmax become, this Vmax dash becomes double, twice of old Vmax, right? Twice of old Vmax. So now for this graph, the Vmax by 2 will be the old Vmax, right here. So again the K0.5 is same, means the substrate concentration where the reaction will achieve the half of the maximum velocity, right? So half of the maximum velocity will be 2 Vm by 2 will be equal to 2 Vm by 2 will be equal to Vm, right? So it is Vm. So K0.5 will be same. And if we use the negative regulator, then the Vmax will be halved, right? Now the Vmax is, for this curve, the Vmax is this, so it is Vmax by 2, okay? So for this case, the again K0.5 is same because the K0.5 is the concentration of substrate where the the reaction will achieve the half of the maximum velocity, which is Vmax by, so this line is Vmax by 4, right? But at the same k 0.5, right? So this curve achieved the half of the Vmax at k 0.5. Positive regulation have achieved the Vmax, the half of the maximum velocity at k 0.5, which is the Vmax here, and the negative regulation achieved the half of the maximum velocity, which is Vmax by 4 here at this at the k at the same k 0.5, right? So here this is example where the k 0.5 has been remained constant, but Vmax has been changed. For positive regulation, Vmax has been increased. For negative regulation, Vmax has been decreased, right? But k 0.5 remained constant for all of them. Okay, understood? If you have any doubt, please ask me. It is clear. Third one,
Yes, sir.
any doubt you have, you can ask.
No, sir. My doubt, I
Yes.
don't have doubt, but I want to say that can't we just see the theta value and just conclude it that more the value of theta, the more will be the velocity.
Can you please repeat it? I mean, you are not audible properly. Can you please repeat it?
Actually, there's a slope. I'm saying about the slope that can we just conclude it and come to the conclusion after analyzing the theta,
Ah, for which range
like
you are talking about?
like the negative one and the positive
Ah,
one. For the value of theta for the negative one is less, and the value of theta is more for
theta means
positive one.
which one is theta?
Uh, I mean tan theta, the slope one.
Acha, slope. Okay, okay. Tan theta. Yes, yes.
So can we conclude from that?
From this curve, from
Yes, sir.
yes, yes. Actually, here, if you will measure the slope, then slope, of course, for this curve as well as here also, the slope is more in the case of positive regulation, because tan theta will be more, right? Uh,
Yes, sir.
with respect to this, and for the negative regulation, the slope is lesser than the uh, you know when there is no regulator. So you are correct.
Yes,
So slope is increasing here and decreasing here. Correct.
yes, sir.
Okay. Any more questions you have?
No, sir. Thank
Huh? Anything you have? Anything else?
No, sir.
Okay. Kuldeep, fine for you? Any doubt you have? Okay. So Abhi, you okay? So I've forgot to ask your background. So you are doing which course and which background you are from?
Sir, actually, I am a second year undergraduate currently pursuing degree in biotechnology.
Biotechnology. Okay, fine. Okay, so last week, yesterday we discussed about the protein structure and function, and in this session we have discussed the enzyme. So I think you missed the last session, but it's fine. I will. So today I will mail you guys, all of you, two of the PPTs of two sessions. Okay, so you can go through that, and if you have any problem, you can ask.
So I have a question that, like, sometimes we have some issues and all. So is this lecture recorded?
Yes, yes, yes. So these lectures are recorded. So uh, shortly you will get the link for the lecture, the session recording repository. So then you will take the recordings also.
Okay, so thank you.
Okay. Okay. So Kuldeep, any question you have? Okay. Okay. So it's fine. So it seems fine. So I think we can close the session. So for your information, that each week Friday and Saturday it will we will start from 8 to 10, both Friday and Saturday, right? So next we will meet on next Friday from 8 p.m. to 10 p.m. Okay, so please join. Okay, so see you on the next week Friday. So thanks for joining.